Welcome to this explainer. I'm so glad you're here today because we're going to unpack something you probably hear about all the time but might not fully understand. We're talking about pH. We'll see how this seemingly abstract math is literally the secret engine keeping us alive, shaping our environment, and even determining what's sitting in your kitchen cabinets right now.
Okay, let's just dive right into this with a bit of a mathematical mystery. It's one that completely trips people up when they first look at the traditional 0 to 14 pH scale. I mean, you see a simple number line, right? It's completely natural to just assume that moving from a pH of 4 down to a pH of 3 means the substance is just a tiny bit more acidic. But as we're going to see, that assumption, it couldn't be further from the truth. To really understand why, we've got to grapple with the truly staggering number, 100 trillion. Yeah, that's a 1 with 14 zeros. See, if we look at the whole range, from very strong acids with huge hydrogen concentrations to very strong bases with almost zero, trying to write out, calculate, and actually compare those numbers in a real lab setting is, well, it's basically impossible.
So here's our game plan for today's explainer. First, the power of 10. Second, how buffers keep us alive. Third, the acid rain problem. Fourth, everyday acids and bases. And finally, number 5, the titration lab.
All right, jumping right into section 1, the power of 10.
So the real magic trick here is that pH uses a mathematical tool called a logarithm, specifically a base 10 logarithm. By defining pH as the negative concentration of hydrogen ions, chemists figured out how to compress that giant, unwieldy 100 trillion range down to the beautifully tidy, elegant 0 to 14 scale we use every day. Instead of writing out an endless string of decimals, we basically just ask, hey, 10 raised to what power gives us this concentration? And honestly, this perfectly illustrates the real-world impact of that math. Because it's a logarithmic scale, we have to use the rule of 10. This means each decrease of one single pH unit doesn't just add a little bit, it actually multiplies the hydrogen ion concentration by exactly 10. So going back to our mystery from earlier, a solution with a pH of 3 isn't just a little more acidic than a pH of 4. It has 10 times more hydrogen ions. And if we drop down to a pH of 2, boom, it's 100 times more acidic than pH 4. Crazy, right? Moving on to section 2, buffers keep us alive. Now consider this absolutely incredible fact. Your body's enzymes and proteins need an unbelievably narrow, specific pH window to actually work. We're talking a blood pH of exactly 735 to 745. If your blood drops below or spikes above that tiny margin, well, your cellular machinery just shuts down. And keeping that rule of 10 in mind, even what looks like a microscopic shift in your blood's pH could literally be fatal.
So that begs the question, how do our biological systems manage to survive when the margins for error are so incredibly thin? Well, the answer is buffers. A buffer is basically a solution that resists changes in pH when small amounts of acid or base are added. Think of them like chemical shock absorbers. They contain both a weak acid and its conjugate base, which means they're constantly on standby, ready to neutralize chemical invaders coming from either direction.
In fact, right at this very second, a specific chemical reaction is acting as a shock absorber in your own blood. It's called the carbonic acid bicarbonate system. Here's how it works. If extra acid enters your bloodstream, bicarbonate ions instantly step in to absorb the excess hydrogen. But if a base enters, the carbonic acid releases hydrogen to neutralize it. This constant, invisible chemical dance is exactly what keeps your blood locked safely right around that 7.4 mark. Okay, let's zoom out a bit for section 3, the acid rain problem. You might be surprised to learn that even perfectly normal, completely pristine rain is actually slightly acidic. It hovers right around a pH of 5.6. And that's totally natural. It's just atmospheric carbon dioxide dissolving into the rainwater. But when you pump industrial pollutants like sulfur dioxide and nitrogen oxides into the air from burning fossil fuels, the rain's pH can plummet to 4.0 or even lower. Now, remember our logarithm rule? That drop from 5.6 down to 4.0 means that acid rain is 10 to 100 times more acidic than normal rain. That is a massive jump. And as you'd expect, this huge logarithmic jump in acidity has some pretty devastating consequences. It essentially leaches vital nutrients straight out of forest soils, completely damaging plant life. It acidifies lakes and streams, disrupting entire aquatic ecosystems. It literally dissolves historical limestone buildings over time. And honestly, perhaps the most alarming part, it causes toxic metals like aluminum to be released from the soil and washed right into our waterways. But
It's not all doom and gloom. This is actually a really triumphant story of science directly informing policy. Seeing the data on these dropping pH levels and all the destructive outcomes led directly to action. In the US, legislation like the Clean Air Act was passed to strictly limit those sulfur dioxide and nitrogen oxide emissions, and because of those regulations, we've seen a massive, highly successful reduction in acid rain since the 1980s, which has allowed a lot of those ecosystems to finally start recovering.
All right, moving to Section 4, everyday acids and bases.
We actually rely on these chemical properties constantly, basically across every single sector of society. I mean, just think about it. In our food, citric and lactic acids give flavor and preserve what we eat. In our medicine cabinets, we keep basic antacids to neutralize excess stomach acid. On an industrial scale, we use incredibly strong sulfuric acid for manufacturing, while agriculture relies on lime to raise the pH of acidic soils. Even the water from your kitchen tap relies on a very careful balancing act of chlorine and sodium hydroxide just to make sure it's perfectly safe to drink.
Which brings us to our final part, Section 5, the titration lab.
Whenever we step into a lab to test pH, we're actually walking right in the footsteps of Robert Boyle. He was an Irish-born chemist from the 1600s, often called the father of modern chemistry. And Boyle totally revolutionized the scientific landscape of his day. Instead of just blindly trusting ancient authorities, he was adamant that theories had to be backed up by precise, careful experiments. Actually, he was one of the very first people to distinguish acids from bases using plant extracts, specifically a dye made from violets that would literally change color right before his eyes when placed in different pH solutions.
So, if you want to recreate this kind of rigorous, evidence-based chemistry yourself, you can do something called a neutralization titration. It's pretty straightforward. First, you measure out 30 milliliters of highly acidic white vinegar and test its starting pH. Then, you carefully start adding a basic baking soda solution, but only in strict 5 milliliter increments. After every single addition, you stir it up, observe the reaction, you'll probably see some fizzing as carbon dioxide escapes, and you test the pH again. You just keep recording that gradual rise until the whole solution neutralizes, right around a pH of 7 or 8.
And whether you're doing a full-blown titration or just having fun testing different liquids, your results are going to align with this pattern. You'll see lemon juice sitting way down low at a highly acidic 2.5, milk will be slightly acidic at around 6.5, and your baking soda solution will be up in the basic range near 8.5. Charting all of this out proves definitively that the abstract power of 10 math we started this explainer with, well, it isn't just theory. It physically governs everything around us, from the sour pucker of a lemon to the neutralizing power of baking soda.
So as you head out into your lab or even just walk into your own kitchen today, I want to leave you with a question. Robert Boyle used violet dye. What tools will you use to uncover the hidden logarithmic scales operating all around you? The chemistry is always there, quietly shaping our entire world. You just have to know how to look for it. Thanks for joining me on this explainer.